welcome to Simcast, a podcast brought to you by the Society for Imaging, Informatics, and Medicine. Greetings, Simcasters. Here's a question for the Simcast audience. Do we need to worry about racial bias in artificial intelligence? In this episode, hosts Prasanth and Mohannad interviewed Dr. Judy Gichoya from Emory University, Chima Okechukwu from the Georgia Institute of Technology, Brandon Price from Florida State University College of Medicine, and Dr. Leo Anthony Celi from the MIT Laboratory for Computational Physiology, as they discuss a groundbreaking paper they published earlier this year. In this paper, they were able to determine how machine learning systems can be highly accurate at determining race. Starting from an accidental discovery to an arduous process of eliminating surrogate indicators or proxies, they were startled to see how robust these model predictions were to signals virtually imperceptible to even expert human observers across modalities as well as anatomic regions. We hope you will enjoy this thought-provoking discussion.
Judy, thanks for joining us with your team. To start things off, can you provide a brief description of the paper and what led you to what you discovered? Was it by accident or were you actually looking for these results?
I thank Mohannad and the Simcast team for inviting us to discuss our reading race paper. And, honestly, it was an accident how we ended up on this path. And that's because there was a call for an article in the Journal of American College of Radiology. At that point, we were working quite a lot with Leo, and I told him, look, I'd noticed that from a datathon that people separated the chest x-rays and the clinical data. And so I suggested that maybe if we looked at a way to combine both, which is an area that we work in a lot, the way we approach our research is to have like the story we want at the end. And the story was going to be, this is going to be another reason why we need more diverse data sets, because this is the only way to do AI, sensible and good AI work. And so we reviewed the papers, picked up a paper that we had looked at from Lale. Then I said, well, we could redo this paper on the Emory data set, which was more diverse in terms of African Americans. And then we would reach out to Stanford, who have the chest expert data set, and get some race labels. And, we thought that would be a good paper. And in the process, we found out that the patterns of disparities, when you look at the true positive rate, which is a good measure if you're trying to think about underdiagnosis in a specific group, was persistent. So the way I like to describe this is, if you had Mount Everest and Mount Kilimanjaro, everyone knows Mount Everest is the highest. So if you are using a data set that was not, from Emory, you still had a big picture showing the disparities. But when we came to Emory, we started to observe some of the patterns were still persisting despite a more diverse data set. I know Brandon has worked a little more to explore this phenomenon, and hopefully he's going to get a chance to explain more of what he found. And so we then started to figure out why was this the case. And also at that point, there was something else that was going on. Leo was very bothered by saying, we're not just going to be the people who say there's this bias. We have to really be the people who say, how do you fix it? And so in this looking for why, one of the teammates, Pochi from Taiwan, came back and said, the models are learning the race. And we said, you made a mistake. And we started repeating all these experiments and recruiting more people, and ended up really finding this very, very surprising phenomenon. And so why does this matter? And this has been, I think, one of the most surprising factors for this, and probably I would say is the biggest takeaway from doing this work, is that even our own team, which has quite a big mix of engineering students and clinicians, the engineering students, it took them a while to understand why this mattered. And while the clinicians were like, wow, and so we found out that the models are able to identify the patient self-reported race. We identify the self-reported race in a legal social construct. For example, if you had to apply for a passport, what you would identify on paper. And we found that this worked for multiple modalities across multiple body parts and generalized new institutional data. That's the biggest takeaway. The most surprising thing was when we cut down on the quality of imaging, where it's barely perceptible to a radiologist that this is a chest X-ray, and the model still found there is information. And so really are the big takeaways from our paper, that this is a task that's done very well by the race models. But the second thing is that when we've always thought that the human beings would be the people that mitigate the bias, it's going to be very difficult to do so for this task.
Yeah, when I read through this, I was completely blown away because it didn't make any logical sense. If you do like a facial bone CT or a head CT, yeah, you could reconstruct what the person looks like through various, even like Terra Recon can do some of these things, right? So we've had that kind of technology before, but these are just chest x-rays, mammograms, extremity x-rays, CTs, nothing, no facial features, no demographic information, all the metadata has been stripped. I had to read your paper a couple of times. I'm like, this doesn't make any sense. How is this even possible? And then you guys go through all of the different steps, like you said, like making the images indistinguishable to the human eye and all these other things to try to see what is it using. And you still couldn't figure it out. I told some of my residents about it and they were asking, what about this? What about this? I'm like, nope, here's where they took that out. It's crazy to think that all of this stuff is somewhere in there. So in addition to removing the metadata, did you guys remove any other attributes? We already talked a little bit about distorting the images, but were there any other attributes of the images that you guys removed or adjusted? Brandon, I know Judy was saying something about your work with this. Maybe you can chime in on that.
Sure. Well, one of the first things we did was we looked at different segmentations as far as removing the lung and just showing as the input, just having the lung segmentation into the model, and then also having the lung removed from the images. And those were both able to have useful information that was able to be classified or detect the patient's race also. In addition, we were able to do a 3x3 occlusion, and we were able to send, just taking out, if you imagine a 3x3 grid over a chest x-ray, the top left corner, the middle left, and things like that. If you remove those different sections, no section particularly had any more useful information than any of the others also. As I think it was mentioned before, we also used a high pass and low pass filter to the point where you couldn't even be able to distinguish that they were chest x-rays, and they were still able to have enough information to be able to, for the model to detect the patient's race, including decreasing the resolution to extreme amounts, really. I think Chima will add a little bit more as far as some of the other metadata that was used to kind of make sure that those weren't attributes used to be able to detect the race also. So I'll let him kind of discuss more on that.
So in addition, we also removed the mass index, the BMI, and ran the model with that. And we also, just to make sure, just to cross our bases, we accommodated for age and sex and bone density as well, and still found that the results were still consistent. I think what was most interesting was the high pass and low pass filtering, because at those points, you pretty much have very, very little details about the image or very limited info about the image.
So why did you choose BMI, age, sex, and I forgot the fourth one? Why did you feel that those things might give some clues to the algorithm one way or the other in being able to detect race? Or were those just things you thought, let's try these? What was your thought process in that choosing?
So part of the reason we chose these ones is because there are some correlations between race and these values, like for instance with BMI. That was what linked us to this one. The other ones were just to pretty much make sure. And like you said, we also ran through internally of things that might be causing these. So these were just some of the things that we thought, okay, these might be possible confounders. So we might as well accommodate for them. What's interesting is we did it both ways. So we also tried to use BMI to predict race and also try to use these values to predict them as well.
Thank you, Brandon and Chima. This is very interesting. I want to turn it to Leo for a moment, and I have kind of a double question here. So can you tell us a bit more about the concerns behind these kind of findings, but also the flip side? Like, could there be practical applications for this, something like validating patient identity, some kind of positive good use of this technology?
Sure. I'm going to start off with an interesting story that I had given in previous presentations. It's the story of Clever Hans, which is an Arab stallion, a horse, at the turn of the 20th century. And he was bought by a schoolmaster. And the schoolmaster taught Clever Hans how to read numbers and how to make calculations like addition, subtraction, even square root. And everyone was fascinated. But it turns out that Clever Hans wasn't actually making the calculation. He was detecting the heartbeat of the schoolmaster and the audience watching. So every time the schoolmaster would point to the correct answer, his heart starts beating fast, as well as the audience. And Clever Hans would think like, oh, this is probably my cue. And when they changed the setup so that the schoolmaster and the audience were not privy to the question that was being asked, Clever Hans was not so clever after all. He got all the answers wrong. And there are examples of Clever Hans in the machine learning research literature. And one that comes to mind is a project from University of Washington, where they tried to teach a computer how to differentiate a wolf from a husky. And it turns out that all the images of the wolves had snow in the background, and all the images of the huskies did not have snow. And of course, the computers learned that and were basing their classification on the background. So this is what we're seeing now, is that if the computers can identify a sensitive attribute, such as the race, it will use it to make predictions or classifications, even if the race has nothing to do with the label. And we think that this is going to happen, that the computers are going to learn what humans do. We make decisions based on the race. We make classifications based on the race. And since the data that we're using to build algorithms are nothing but encodification of what we do as captured by electronic health records, I could guarantee you that the computers are going to do the same. They're going to make decisions. They're going to make predictions based on an attribute that is not related, that should not be related to what you're trying to predict or what you're trying to classify. So we needed to spell that out of why this is important and why this could potentially be a big stumbling block for artificial intelligence, because we have to be aware that the ingredients for artificial intelligence is real world data. And real world data is just laden with this subjectivity and biases and prejudice. So don't be surprised when we discover that all our algorithms at this point are all as biased and as prejudiced as humans. And I think we really need to take a pause and understand how computers are making decisions before we implement them. As far as, is there anything good that could come out if you teach computers how to detect sensitive attribute? I would say that you could do this as a check to make sure that you are removing whatever is being used by the computer. So going back to the example of the huskies and the wolves, so that was easy to fix. You remove the background and you retrain your algorithm, and the algorithm will now focus on the features of the animal rather than the background. But how could we do that with imaging? We don't know how the computer is learning the race from the imaging, so we don't know what to remove. So I think teaching machines to identify these attributes would allow us to remove what those attributes are before we train it to make a classification or prediction. That's the good thing that I could think of. I think we should routinely do this so that we could fully interrogate an algorithm before we implement that, and that those algorithms will not widen the disparities that we're seeing now.
All right. Thank you for that answer, Leo. This is fascinating. I'd like to turn it to Brandon and ask a question. So what I noticed reading the paper is it looks like the data set is mostly from a radiation-based imaging modalities, X-ray and CT. Now, forgive me, I'm not clinical, so this may be a dumb question, but I'm curious. In your opinion, did you try to do this with something that's based on MRI, like magnets or ultrasound? And if you didn't, can you speculate what that might look like?
So with the manuscript, the preprint that we have now, it wasn't included, but it was something that we wanted to look at. However, we just didn't have the labels available at the time. But since we've released the preprint, we have had some other groups of researchers, one led by a group in England that looked at using the MRI modality for head MRIs. And there was some correlations that they found as far as using those images to be able to detect race. And in addition, another group was able to detect race with echocardiograms. And then also in a non-radiology domain, this is a paper that was released just, I think, a couple of days ago by Dr. Coiner and his group. And they found that a model can predict a patient's self-reported race from retinal images as well, even after the pixel brightness and vessel width has been normalized. So it seems that some of these signals and features are more prevalent than we ever originally imagined. And you really kind of need to look at these and evaluate your models and how they perform with different groups before releasing them in the wild in clinical settings.
It's interesting how this is kind of embedded and just definitely highlights the need to run your algorithms on, more and more diverse data sets. Something that Leo had mentioned kind of caught my attention about, how do we remove information or bias from the algorithm when we don't know how it's getting it? I mean, would you think about could you subtract, you've got your algorithm. So mathematically speaking, right, you can do subtraction, one algorithm to another. Obviously, this is a very big oversimplification, right? I get that. But is that something that you guys think might be possible in the future, where you've got a race detector and then you've got your regular algorithm and then you do some sort of subtraction and then run the data again so that it can be cleaner in a way so that you can remove that bias? I don't know. What are you guys' thoughts on that? Maybe Leo, we can start with you.
I mean, it really depends on what the race detection is using to make that classification. We do have a hypothesis that we think might explain this phenomenon that we have discovered. This is related to how medical equipment are designed, or in general, how medicine is designed. So as we know, a lot of the research that is the resource for the tests and treatments that come into practice is based on studies coming from a few rich countries. And in those rich countries, the participants are predominated by the white male population. And this is the way that equipments are also designed. When they make an X-ray machine, when they make a glucose monitor, they have some index people that they design the machines around. And we think that the machines that take X-rays and CAT scans and MRIs are optimized with white people as the index cases. And maybe the computers are detecting that this image is suboptimal. This is not the type of individual that this machine was optimized for. And it's detecting the noise rather than specific features in the images. That becomes an issue, right? How do we fix that? I like your idea of subtracting the algorithm that detects race from the algorithm that provides a particular prediction or classification. If our hypothesis is correct, then that may not work. And the solution for our hypothesis is that we start really being more inclusive in who we design medicine for. So research should be more inclusive in terms of where the studies are being performed. Equipments that are being manufactured should be more inclusive in terms of who they should optimize the medical product for. And unfortunately, I don't think machine learning can fix that. I think that is going to require a major overhaul of how we perform research and how we design healthcare delivery as a system. But at least we were able to, discover this finding. I mean, it's not a new finding. We kind of know this. We know that the drugs that we're using for high blood pressure or for diabetes, they're based on studies primarily done in the US. And we just think that our understanding of diabetes would apply to the rest of the world. But that clearly has to change. Whether machine learning has some role in achieving that objective, we don't know. But I think this is a problem with a social cost, and machine learning at most may help us understand better what are the intricacies and the complexities of the problem. But I doubt that machine learning alone can help fix the problem.
Yeah, it's interesting because I get what you're saying, particularly around studies, but If you look at the hardware, it may have been designed in the United States, but a lot of the electronics are made overseas, or some of them are designed overseas in some Asian countries and things like that. And, a photo is a photo. It doesn't necessarily matter if it's Kodak, Sony, but, they may have different algorithms and things like that for the post-processing on the inside. So it definitely becomes a more interesting question of like, where in this process is that bias being put in by people, even though we think of it as an electronic device. Brandon, Chima, or Judy, please weigh in on this. We'd love to hear what you guys also think about this idea.
Yeah, I don't know why Leo is not using his usual pulse ox example and how this actually ended up failing here. And one of the things that we've tried to do actually, you're right, Prasanth, it's just about thinking about the pipeline and where things fail, right? So in the paper, we describe a lot of how the experiments we did for looking at as to why, right? Thinking about breast density, thinking about bone density, thinking about diseases, right? Maybe that one group has a higher burden of disease than another. Segmenting the lines and, looking at tissues, even putting corners and boxes on the chest X-ray and seeing which one contributes the most. And honestly, none of those experiments have been able to help us figure out the why. There was an earlier hypothesis about melanin and interaction with X-rays, but one of the things that among the data sets we used is the digital hand atlas. And the way that data set is done, it's a photograph of an X-ray. So you would assume that with the picture is taken, that degrades, the quality is different. And I know that Brandon actually did run on the Text Expert digitized versions of the images. So, and then when we saw the same pattern on ultrasound and MRI, then that sort of interaction, melanin interaction with X-rays, theory, honestly, is down on our list. And so one of the things that I've done is to get phantoms. We're still analyzing the data, and it's actually pretty interesting, right? But it turns out that there are not many phantom images that are available to people. I think people got them a lot, actually. Maybe because it can give you a sense of the quality of imaging in a practice or something like that. And so right now I'm trying to get more, but we were able to do some studies with varying physics protocols, and the results were interesting. I don't want to just start to discuss them right now because it can be derailing, but it was one phantom, but we have sort of representation across races. And so it's going to be interesting as we unpack what this means, for the explainability angle.
Why did you guys pick race? Why not age or biological sex? Not gender. I know that's a whole different social construct, but biological sex is less of a social construct. So why did you go down this path instead of a different one?
Really, like I said, it was an accident. We were trying to answer the why for why the biases persisted despite a more diverse data set. So the biases were on racial lines. They weren't on, men versus women primarily. And so that's really the reason. But other people have done the age and sex, I think, and biological sex. I know that Paulie is one of those people. I think they did some knee MSK stuff that showed this. I believe that we'll see quite a lot of work done around this area. Obviously, we know that all those issues are very controversial, because we've seen previously AI systems used to identify people who identify as LGBTQ. And so quite a slippery slope, but it was just sort of, we were following the line of our questioning from our original question.
And I just wanted to add that it's not just race or age or gender. We're very paranoid that the introduction of algorithms will really encode our prejudice against populations that are typically marginalized outside of those demographics. For example, in the intensive care unit where I work, we know that there are disparities in outcomes when it comes to patients who are IV drug users or alcoholics or morbidly obese, or they have mental health problems. And so the first thing that we try to do is, what is the degree of disparities that exists in your data set? And that is, I think, a key message that we would like to give to the machine learning community, that even before you start doing exploratory data analysis on the data set that you you try to figure out were there biases and prejudice that selected the patients and allow them to come into your cohort. So going back to the intensive care unit example, are there populations who die before they even come to the ICU? Are there populations who don't have access to the hospital? And what would the impact of excluding them from your data set? What would the impact of that when an algorithm is suddenly deployed? So the first step is really understanding what prejudice and disparities that exist in the data set and be cognizant of that throughout the entire life cycle of developing and evaluating and monitoring your algorithms. And then be very paranoid about the effect of your algorithms on this population. So algorithms are not a finished product. As you know, once you deploy them, you have to continuously monitor them. I know that you have to monitor them for accuracy because there's such thing as calibration drift, but more importantly, what is the impact of this algorithm on existing disparities? If the disparities are widening, if only a certain group of the population is benefiting from early detection of sepsis, then you have to recalibrate your algorithm because in the end, you're not going to move the needle.
So this brings up an interesting point about study design, obviously. Like, say I've got an algorithm and I've done all the things you talked about, right? I've vetted the data sets to make sure I have a nice broad population base. I might even get international data, right? But kind of looking at what your paper is saying is even if I do all those things, the machine still somehow magically, in a spooky way, is determining race. So what does this kind of mean for future algorithms, even if you do all the right steps? Like how, other than trying to mitigate it, on the back end, like we talked about a little bit with maybe a subtraction kind of thing, does this just mean like every paper you read about a new algorithm, you have to take with a grain of salt, or you just have to say like, okay, they probably aren't covering everything. So how much more can we trust these algorithms, even if we're doing everything right?
So even if you're doing everything right, as I mentioned earlier, it doesn't end there. They have to be closely monitored forever and ever, and they have to be recalibrated because, as we know, their impact would be different as soon as there are some changes in the practice patterns. So I don't know the answer of how to fix things. We do know that the way we are developing algorithms now is not adequate. And we do know that we're not prepared yet for implementation until we completely understand how the computers are making decisions or classification. And our paper is really a call to action. It's really soliciting input from other brilliant minds out there. We're making the data sets publicly available. We're making our codes also available to other investigators so they could improve upon, they could do more experiments. But it will take a whole village to address and solve the problem that we have now. So again, just because an algorithm is accurate, so you can make sure that every demographic is represented in the data set, but that is not enough because if accuracy is your only metric to gauge whether it is a good algorithm or not, then all we're going to be doing is perpetuating the status quo. So somehow you would like to come up with a prediction that would be the outcome if the world were fair and everyone has equal access to healthcare. But those data sets don't really exist. And is there a machine learning solution there? Like, what if I change the attribute that is being used by the computer to detect race and fool the computer that this person is white rather than black? Would that change the classification? Would that change the prediction? So those are some of the things that we're thinking about. So some adversarial attacks on the data set, adversarial attacks on the algorithms. Is that a part of the solution to fixing the disparities that we're seeing now? So in a bank loan algorithm, what if I change the zip code of this person who's applying for a bank loan and it becomes a zip code from a wealthy community? Will that change the decision of that algorithm? These are very complicated questions, especially from a machine learning standpoint. And we're hoping that more people will contribute to trying to address these challenges to implementation of algorithm based on real world data.
Thank you, Leo. This is quite fascinating. So one thing I'm curious about as I hear you covering this, you're saying that you're throwing the images at this algorithm and the algorithm seems to just pick up the race always and reliably. Do you have any clues to what it is that it might be picking on? Facial features, skin tone? I know skin tone isn't really a factor here, but I'm just giving random examples. Could you put a finger to any what's going on behind the scenes here, either yourself or Brandon?
So that's a really good question, and one that's kind of on the top of our minds. And Leo and Judy mentioned some of these already, some of the hypotheses. And hopefully if we could discover what the signal is that's contributing to this, we could address it and hopefully be able to mitigate some of the bias that we're finding. But I think one of the things that the study has confirmed for us is that traditional grad cams don't seem to work well with explaining what the model is learning or as far as features. And we've had some researchers reach out to us, and they're hopefully using some novel methods that they're developing to hopefully address this explainability issue with the race detection. And one of the other things I wanted to mention too is one thing that we found in the paper was when we trained a model to detect pathology like pneumonia, and then we froze the model and then added a softmax classification layer to retrain the model for race, it still performed well at detecting the race. And it seems that maybe the model was learning features when learning pathology that were also useful in detecting the patient's race. And I just wanted to say, this wasn't included in the paper, but we did another experiment after the paper was released. When we trained the model for other tasks, such as determining if the chest X-ray was from the front or the back, when it does that task and then we freeze it, it doesn't perform nearly as well at detecting race as when we train it to detect pathology. And we're having a lot of internal discussion on that topic and what it means, but I think it's a big potential concern for future development with medical AI.
That's definitely interesting. Chima, I was wondering, how does this algorithm differ from other algorithms like facial recognition software that, that's already out in commercial use? What makes your algorithm more prone or special for this work?
So actually, it's funny because our algorithms, the way we built our models were not anything special or intentional. We really just use basic models or pre-trained models from already available frameworks like Keras or PyTorch. We just pass the training through them. Any good deep learning model, we try to cross so many deep learning models as well and still achieve very good results across the board. So I think the problem with facial recognition is that it's actually been well studied and well versed. So there's a lot of data on it. Like right now, we understand that how we do facial recognition is first you identify the lines, and then you identify combination curves, and then finally you build something like the eyes, the mouth, the nose, right? But unfortunately with this one, we stumbled across this by accident, and we'll probably need more to truly understand what models we're picking up.
Yeah, this is quite the quandary. We've talked a little bit about some of the positives, and Judy alluded to some privacy concerns earlier on. At a larger population, Emory or Stanford, like you guys get your data sets, this kind of thing may not be as much of an issue from determining race per se, but so a large percentage of our population is rural. I'm originally from the state of Maine, and when I took a case to at the time, AFIP, now it's renamed, but the pathology course that us radiologists take, I took a very run-of-the-mill, it was a liver hemangioma. But I couldn't get in touch with the patient to get consent. So I contacted our institutional IRB, and they asked, well, how rare is this disease? And I said, no, it's fairly common. I gave them the information, and they said, okay, because if this is a rare disease, that in of itself can be identifying. So I guess the question of when it comes to privacy and things like that, like if you are a non-Caucasian for example, the state of Vermont is 98 plus Caucasian, right? So suddenly if the algorithms are detecting the race, they could potentially pinpoint you as an individual to some degree, right? What kind of privacy concerns or things like that do you see with this kind of information that you've found through your research here? Judy, would you like to kick us off on that?
The thing is that I don't think anyone right now has been able to go back and get consent on all this AI work that we're doing. Definitely, there's a bigger role for patient engagement to understand what projects and things are being done with their data. You know that this is under review and this is just in the public domain. We did get a lot of public comments, and including some racist ones. And so some of their views were saying, well, finally we can prove that race is biological, else why would it be able to detect this, And then also think about some of the things that, make you whatever you self-identify as. So maybe that my skin is a little darker, I may identify as African American, but if I was a little bit on the lighter side, I may decide to identify as white or a mixed race, right? And so, by sort of labeling people this way, you could say that people should have the opportunity to change these records in the electronic medical record system to wherever they want, if they decide that they want to self-identify differently in a few months or years. And so I think there are many, many ethical questions that have to be answered around this. We know that not just this part, but there's quite a lot of projects that have shown that you can re-identify open, data in the public domain. And so I would say that luckily for right now, we don't have any direct complaints from a patient or something like that. And then number two, I think we are very cognizant and are actually collaborating with a couple of ethics teams to try and explore this more and bring this discourse. Obviously, ethics takes quite a bit to come to a consensus, but these conversations are happening. And then we also do need to necessarily actually reach out to patients, but also how do you discuss some of these challenges when it comes to patients? So think about this, Prasanth. So if I call you, I'm calling about to tell you that, I used your mother's x-ray to tell you about their race, and your mother passed away or had a terrible experience in the hospital. That's actually pretty more harmful to try and bring that stress to you. I think that the IRBs have to evolve to be able to allow us to do this type of research in a safe way where we put the patient's interest first. But I don't know that today we've established how patients can even challenge. For example, if you think about the legal AI systems, if you deny me a bond and say that this is machine driven, do people even have ways to challenge those decisions? And I think we're quite a long way in terms of exploring those patient interactions and society implications of massive rollout of AI for medical imaging.
So I think everyone has pretty much talked about it, but the results highlight the importance of designing for underrepresented groups as well. I think there are a lot of models out there, and one thing we urge them is to see how the model performs across different groups, sex, race, and gender. AI and race have typically had a touchy relationship. If you think back to mishaps with Facebook, Google, and Amazon, their algorithms. But fortunately for us, this is not one of those cases, and it's more of highlighting some potential problems. So.
Thank you, Chima. And thank you, Brandon, Leo, and Judy for being with us today. This has been a very interesting conversation. I think the three of us, the hosts, were very excited when we read about your paper. So we appreciate you making time to talk about this paper with us today. And we will hopefully hear more from you in the future, because it sounds like you still have some intriguing questions to explore. So thanks again, and have a great day, everyone.
Simcast has been brought to you by the Society of Imaging Informatics and Medicine. Please visit our website at siim.org for more information and educational content, including webinars and an archive of prior episodes. Please follow us on Twitter at sim_tweets. Thank you to our listeners for your continued support.